Dear students, today we will discuss the third law of thermodynamics. Third law of thermodynamics is related to the entropy. Therefore, before going to the third law of thermodynamics, we have to understood the entropy. For this law, entropy is taken as the randomness. When there is a randomness is more, then the system has the higher entropy. And if randomness is less, then the system has the lower entropy. If suppose we have a S2 is there, one S2 in the ice form, okay, total ice is there, that is the solid ice form H2O, then liquid H2O, and there gaseous form of H2O is there. The randomness is increases in a vapor form H2O, then this and then this. Therefore, entropy of this system is higher than this, and entropy of liquid is higher than this solid. Okay, as the temperature decreases, you found that entropy goes on decreasing. Okay, at a particular, when you decreases the temperature, makes our matter or the substance cold and cold. All the substances at very cold or very low temperature becomes solids. Therefore, when you make temperature lower and lower at a particular temperature, that is absolutely 0 degree Celsius temperature, the entropy of the perfectly crystalline substance becomes 0 at absolute 0 degree Kelvin Celsius temperature. 0 degree Kelvin temperature. Okay, that is our third law of thermodynamics. When you decrease the temperature of any body, it becomes solid and it's obtain the crystalline, perfectly crystalline body, and therefore we define the third law of thermodynamics as the entropy of the perfectly crystalline substance becomes 0 at absolute 0 degree Celsius temperature. Therefore, the use of third law is to find out absolute entropies. Absolute entropy means the at absolute 0 degree Kelvin to the T degree Kelvin temperature, the change in entropy is called as the absolute entropy. And this absolute entropy we can find out by using the third law of thermodynamics. Now, the entropy, very small entropy, very small change, okay, D stands for the very small change or difference of entropy, very small. Entropy is denoted by the S, remember that, entropy is denoted by S, and only change in entropy can be found because entropy is a state function. Therefore, only change in entropy we can find out. Therefore, very small change in entropy is given by dq upon T, which is formula for the entropy. Now, we have known that the molar heat of capacity is given by the equation dq upon dt. Therefore dq can be given as, by transferring dt to this side, dq is equal to cp into dt. Putting equation 2 in equation number 1 as dq, okay, this dq we put in this place. Therefore ds, very small change of entropy, is given by cp into dt upon t. Okay, this change is the very small, that is infinitesimally change of entropy. It means it's given by this. Okay, if suppose our entropy is start from 0 to T degree Kelvin temperature, then at each step there is a change of entropy is there, and all the entropies collect together, we can find the entropy at the T degree Kelvin. Okay, this very small change, okay, very small change of the entropy, very small change temperature is also there, we can calculate it by using this equation. Okay, this is the very small change of entropy. ds is equal to cp into dt upon t. Okay, total change of the entropy from 0 to the T degree Kelvin, okay, that is means that at the T degree Kelvins we can find out the integrating this equation number 3. Okay, integrating above equation, we can find out the absolute entropy of a system from which start from the absolute 0 temperature to the T degree Kelvin temperature. Okay, now integrate ds. Okay, our entropy at the absolute 0 temp will be the S is equal to 0 to the S is equal to T. Okay, at T temperature. And according to the third law of thermodynamics, at the absolute 0 temperature, S is equal to 0, is equal to integration of this term Cp into del T upon T. This becomes equal to also Cp into ln dt. Okay, this is also equal to this, because integration upon 1 upon t is equal to ln t, and integration of d ln t also ln t. Therefore both these quantities are the same and integration of both will be same. Therefore this becomes equal to this. Okay, these are the one and the same equation forms. Okay, now for this we can say that yes, our entropy at T degree Celsius temperature and minus entropy at the absolute 0 degrees Kelvin or Celsius temperature is equal to Cp ln dt, and is equal to St is equal to integration of Cp ln dt. Okay, now the integration, the value of integrals can be found by a graph Cp versus log t. Okay, this ln means we can convert ln into the log. Okay, therefore by a graph Cp versus log t, the graph is looking like that. At the A, at the B and the C, A is here at the 0 absolute, and T at the T temperature, and B is at the T1. Okay, our entropy at the point C at temperature T is given by this way. Okay, the values for this or solution for these integrals can be given the area under the graph is gives the solution for these integrals. The value of Cp L and dt will be the area under this graph. Okay, there is second graph is also Cp versus temperature. It becomes looking like that. Okay, as the temperature increases, our molar heat capacity increases. Okay, Cp stand for the molar heat capacity at a constant pressure. Okay, this we obtain. Now we can find out entropy S at temperature T by knowing the values Cp at temperature ranging from 0 to T degree Kelvin or temperature. Okay, the entropy we can find this entropy by the values of Cp and all the temperature ranging from the 0 to T degree Celsius. We can find out the entropy is at temperature T. Okay, this is the absolute entropy. Absolute entropy will define the entropy difference or entropy change from absolute 0 temperature to a particular T degree Kelvin temperature. Now we have the equation. This by simplifying, if suppose we simplify the equation number 4. Okay, find out the integration for this equation. St is equal to Cp is the constant for the integration. Constant integration. We have no integration for the constant, therefore Cp is put as it is, and integration of L and dt is equal to d L and t. Okay, for this d L and t you have to check it. Integration of derivative of d L and t, Cp d L and t, Cp d L and t. Okay, therefore integration of L and t becomes the L and t, and when we simplify this equation, St is equal to 2.303 Cp log t. Okay, we change the base of log. Okay, ln x, if their value is there, then 2.303 log x for the solution for this. Like that way, ln t is can be converted to 2.303 Cp log t. Okay, this when we consider the Cp is a constant for temperature ranging from T degree 0 degree to the T degree Kelvin temperature. Okay, like that way we can find out the Cp as a constant. Then this equation can be used, and by using the Cp values and T values we can find out the entropy of a particular temperature. But it is difficult to find out Cp values from 15 degree temperature to the Kelvin temperature to the 0 degree Kelvin temperature. It's difficult to find out the actual value of Cp. Okay, therefore for the find out actual value of Cp, we have a rule, that is a Daba T cube rule. By using the this rule is stated as your entropy is equal to A into T cube, and A is the constant, can be calculated by at any low temperature T, we can find out the Cp values, and by using the Cp values we can find out it's a constant. A is the constant for a ranging from 0 degree to the T degree Celsius temperature. Okay, now we have a substance which is at 0 degree Celsius temperature or absolutely 0 degree Celsius temperature, and B, from B it goes to the C. The temperature correspond to the B is T1, and temperature correspond to the C is the T, and the entropy of C we have to calculate it at the T temperature. The entropy changes from A to B, B to C, from absolute 0 temperature to the T1 to the T1 to T. The entropy of C can be calculated. Now for this temperature, okay, we are from 0 to the T1 temperature we use the Daba cube rule, because for find out the perfect values of Cp we use the Daba rules from 0 degree to the something T1, that is round about to the 15 degree Celsius temperature. We use the Daba cube rule. Okay, now total entropy of this system will given as S is equal to integration of Cp into dt upon T. Okay, that particular equation we use. Okay, this equation we use one and the same. This equation and this equation is the one and the same. We use this equation. Okay, dt upon T. Okay, plus integration of Cp. This equation we will use Cp ln d ln T. Okay, this is the equation we will use now. Then by putting the Cp values is given as S is equal to AT cube dt upon T plus Cp del ln T. Okay, thereby solving this, S is equal to T cancel, AT square dt plus Cp d ln T. Okay, now by solving this, integration of x square is equal to x raised to n plus 1 upon n plus 1 by using this rule. Okay, t square for t square is equal to, our values will be a t raised to cube upon 1 upon 3. For we solve this equation for find out the Cp's value. For Cp value it is difficult to find out the from 0 to 15. Okay, in this case 0 to T1, in this case were T1 to T, 0 to T1, T1 to T. Okay, limits. Then plus, okay, we find this value plus Cp d ln T. Therefore AT square we have known that AT square is equal to Cp. Okay, therefore Cp 1 by 3 Cp plus integration of Cp del ln T. Okay, this is the equation. We can find out the entropy of a substance from ranging from temperature absolute 0 to the temperature T. If during this temperature 0 to T there is if allotropic changes is there, okay, 0 to T degree Celsius temperature, if there is allotropic changes between the substance found, then we have to add one of the values, that is the delta H transition to the T temperature. Okay, this is the extra values we have to add delta H T upon T temperature. This is the transition, that is allotropic transition of the substance if takes place there, therefore additional value delta Ht upon Tt is added in this equation. Okay, now we are interesting to find out the entropy for liquids and gases. Okay, suppose our liquids is starting from the absolute 0 degree Celsius temperature to the a T degree Celsius temperature. Okay, therefore at the first change there is liquid is the melting, solid at absolute 0 temperature, there is a crystalline solid is there. Okay, we have a gas, we have to find out the entropy of gas or the liquids. Okay, the such transition is found there. Okay, at the your temperature is increases, the solid get melts, again temperature increases, the liquid gets boiled, then at the temperature T you have to find out it's converted into gas, you have to find out the entropy at that T degree Celsius temperature for a gas or the up to this for the liquid. For this first case, therefore the entropy of liquid and the solids we can find out by the summation or the sum of all the entropy changes of that particular substances which transfer from number of stages from solid to the liquid to gases, all the entropies, total sum of all these entropies, we will get the entropy of a particular liquid and the gases at the T degree Celsius temperature. Okay, during first conversion or during transformation of first from 0 to the its melting point, the first entropy, heat of entropy is given as integration of Cp ln dt. Okay, entropy of heat change is given as, for the first change during the 0 to its melting point, is S is equal to Cp ln dt. Okay, during this the entropy. Entropy at the melting point is given by delta Hm upon Tm. Okay, at the Tm degree Celsius temperature, your crystalline solid is melts. Okay, and this Hm is the latent heat of melting. Remember that. Okay, during the first stage 0 to melting point, the entropy is given by our previously derived equation of previously integration. We can find that S is equal to integration Cp ln dt. Okay, then next our entropy of melting S is equal to is given as delta Hm upon Tm. Okay, delta Hm is the latent heat of melting. For the third stage, that is Tm to the boiling point Tb, the its temperature is the, you consider 0 to Tm. Then second is the Tm to Tb, integration of Tm to Tb. During this it is given by Cp ln dt. At fourth stage we give the entropy is equal to delta Hb upon Tb. Hb is the latent heat of vaporization. And this temperature is the boiling temperature. Okay, this is the boiling temperature for a solution. Okay, now we start to find out the entropy of a gas. Okay, therefore we said that the entropy of liquid or gas is can be calculated as the total entropies are sum of all the entropies during the substance is transformed from one state to the other state. Okay, in this case, substance at the 0 to it transfer to the melting point, then boiling points, then the at particular temperature. Okay, during 0 to boiling points, there is a entropy is the integration of Cp ln dt 0 to Tm. And at the melting point, delta Hm upon Tm, that is delta Hm is the latent heat of melting, and the entropy is given by the change in entropy is given by the delta Hm upon Tm. For this is given by the delta Hb upon Tb, that is this is delta Hb is the latent heat of vaporization, Tb is the its boiling point. Okay, during Tb to the particular temperature, its integration is given as the Tb to T temperature integration Cp ln dt. Okay, therefore during the 0 degree Celsius to a T degree Celsius for a gas, there are number of transformation is there. The first transfer 0 to melting point, the entropy is given by Cp ln dt. At a melting point, the change in entropy or S is given by delta Hm upon Tm. During the Tm to the melting point to the boiling point, there is a entropy Cp ln dt for third step. Fourth step, at the boiling point, entropy is delta Hb upon Tb. And at the last step, from particular temperature T, Cp ln dt. Suppose we have to find out a gas at the 25 degrees Celsius temperature, 1 atmospheric pressure. We found out the entropy, then entropy of that gas we can find out the summation of all the entropies during which the substances is the changes from one state to the other state. Okay, now the total entropy change is given by total entropy for a gas is given by integration of 0 to Tm. Okay, first ln dt, then plus delta Hm upon Tm. Okay, that is this is our that is called as the entropy of melting point. Okay, and this is the entropy of boiling point. Entropy of boiling point. Okay, therefore we first during to the 0 to the Tm is the entropy Cp ln dt plus at the melting point delta Hm upon Tm is your temperature is the Tm to the 0 to the Tm. Okay, in this case also 0 to the Tm, and during this 0 to the Tm degree Celsius plus our third Cp ln dt plus delta Hb upon Tb plus Cp ln dt. By using this equation we can find out the total entropy at T degree Celsius of a gas or the liquid. This is all about the how we can find out the absolute entropy. Absolute entropy means the entropy change from the absolute 0 temperature to the T degree Celsius temperature. Okay, in this case 0 to the T degree we can find out the summation of all the entropies for a liquid or gases during the transformation from the a states of substance to the other substance. Summation of all we can find out. That is all about the third law of thermodynamics. Thank you very much.